Audio Jungle. Audio Jungle.
Alright, so now we'll have to draw the stage velocity triangle, okay, or velocity triangle. AXIAL, okay, AXIAL flow compressor. All right, and what velocity triangle we are going to draw? It is for stage. If I say stage, it means we have a rotor and we have stator 1, 2 and 3. So if you check 1 to 2, it is rotor, okay, and 2 to 3 it is stator. All right, rotor is a rotatory part, okay. So if you want to write that enthalpy for this rotor and stator, so how you will write that? Okay, so that is again, because why once you go for the work and all, then that time enthalpy is what required, okay. So that's the reason if you write the enthalpy balance across stator and enthalpy balance across rotor, so it will be better here only, okay. So enthalpy balance across rotor. So where is the rotor? Check, it is 1 to 2. So I can write enthalpy across, total enthalpy obviously it will be constant, H01 and H02, because where is the rotor? Rotor is what in between 1 and 2. But as I told you already, this enthalpy is total enthalpy, but for the rotor always remember the quantity will be recognized by the rotor only relative quantity, okay, relative. So H01 relative, okay, is equal to H02 relative, or you can say total relative enthalpy must be constant across the rotor, across the rotor. This is very important, okay. Across the rotor total enthalpy must be constant, but what enthalpy it is? Relative enthalpy, relative. Why? Because it comes from the relative velocity. Now if you write what is the H01, okay, so if you write H01, that relative enthalpy, so what will be the formula? The formula will be H1 plus that velocity, and what velocity it will be? relative velocity, omega 1 square by 2. In last class I had explained W1 and W2 was relative. Similarly, if you write H naught 2 in velocity, I will draw velocity triangles, you will understand. Last class I had drawn, so I believe that you remember that. So this is nothing but H2 plus omega 2 square by 2. So as you know, H naught 1 is equal to H naught 2. So what will be the formulation here? H1 plus W1 square by 2 is equal to H2 plus W2 square by 2. So this is very important, okay? This relation is very, very important. Across rotor. Alright. Similarly, you can write the enthalpy balance. Enthalpy balance across stator. Where is the stator? 2 to 3, right? So stator. So stator is what, between 2 to 3. Hence the enthalpy H naught 1 is equal to H naught 3. So what is the mean of it? What this enthalpy? This is the absolute enthalpy, okay? Because in last class I had given one table and I told you stator will recognize absolute velocity, it will not recognize relative velocity, okay? So H naught 2, what will be the H naught 2? So H2 plus, what is the absolute velocity? If you remember, it is C2 square by 2 is equal to H3 plus C3 square by 2. Okay, so need to remember this, and what I am writing here, these are very important, and I will be using this equation in next equation required once you go for degree of reaction and work analysis. So we will get that. So this one I have given for just because single marks question they can even I think recently they had asked also. So across the stator, what enthalpy will be constant? So you have to say across the rotor stator, absolute enthalpy will be constant. Okay, H naught absolute will be constant. Always remember. Across the rotor, what enthalpy will be constant? So across this rotor, relative, total relative enthalpy will be constant here. Right. Remember, I am saying total enthalpy. These are the total enthalpy. Okay. H naught is total, or better I will write specific enthalpy, and this enthalpy is nothing but H naught. Okay, and H naught here it is related to the stagnation. Stagnation enthalpy. You cannot say static enthalpy will be constant. I am talking about the total enthalpy, it will be constant. Both side you can write total, or both side you can write a specific, but it is the total value. Okay, it is not static. My point is to tell you not static enthalpy is constant, total enthalpy must be constant. Okay, that's the point only. All right, now we'll draw the velocity triangle, and in velocity triangle here the heading I have given to you, this one. So we'll go for the, see this table I had given last class. So we need to draw the velocity triangle, and from the velocity triangle we'll go for the further analysis. So if you draw velocity triangle now, so hope now you are master like how to draw this velocity triangle. Now it is very clear, no, to all of you. Okay, alpha 1, beta 1, c1, w1, wt1, ct1, u, alpha 2, beta 2, w2, c2, ct2, wt2, u, and obviously this is the ca, axial velocity. So from this triangle, if you check, this is the inlet triangle, and this is the outlet in triangle or exit triangle. Exit to what? Exit to rotor. This rotor blade is what? Rotating. So now if you check, what is inlet triangle? It is nothing but CT1 plus WT1 is equal to U, equation 1, and outlet triangle it is CT2 plus WT2 is equal to U. Okay. Now from equation 1 and 2, what you got? CT1 WT1 is equal to CTT2 plus WT2, or you can write CT2 minus CT1 is equal to WT1 minus WT2. This is very powerful result. Okay. Check here in this triangle. In this triangle you can check what is the tan alpha 1. Tan alpha 1 is nothing but CT1 divided by CA, or CT1 you can write CA tan alpha 1. Similarly, tan beta 1, check, tan beta 1 is nothing but WT1 divided by CA, or CA is equal to, sorry, WT1 is equal to is equal to CA tan beta 1. Okay, so this is the value of CT1, this is the value of WT1. Now coming to this tan alpha 2, it is CT2 by CA. What is CT2? CA tan alpha 2. Similarly, what is the tan beta 2? It is WT2 by CA. What is WT2? It is CA tan beta 2. Check this. Okay, from the velocity triangle. Now use this CT1 WT1 CT2 WT2 value. What you will get? If you write CT2, then CT2, what I remember, it is CA tan alpha 2. What is CT1? CA tan alpha 1. What is WT1? CA tan beta 1. What is WT2? CA tan beta 2. You know CA is common because it's an axial machine, so definitely velocity will be constant for inlet and outlet triangle. So what you will have? Tan alpha 2 minus tan alpha 1 is equal to tan beta 1 minus tan beta 2, or tan alpha 1 plus tan beta 1 is equal to tan alpha. This result is also very useful. Very useful, okay? Very useful result. Alright. Now if you check, this is the equation 1. So from equation 1 you can see from equation 1. What is the equation 1? CT1 plus WT1 is equal to U. It is CA tan alpha 1 plus CA tan beta 1 is equal to U. Tan alpha 1 plus tan beta 1 is equal to U by CA. This is also very important relation. Okay. Whatever the box I am giving, it is very useful formula for the numerical. From equation 2, what is the equation 2? It is, check the equation 2, CT2 plus WT2 is equal to U. What is CT2? It is CA tan alpha 2 plus CA tan beta 2 is equal to U. What is tan alpha 2? U by CA. This result is also very important. Or what you can write? You can write tan alpha 1 tan beta 1 is equal to tan alpha 2 plus tan beta 2 u by c. Remember this result. This result will help you to solve the problems. Okay. So this is the alpha 1 beta 1 alpha 2 beta 2 relation. Now with the help of this relation, velocity triangle, we will write the Euler's equation of turbo machine, or simple you can say Euler equation for the compressor will write simply. Okay. So next, what is the equation? The equation is called I hope this one is very nice and very clear to all. We can say the Euler equation for compressor, or Euler equation for turbo machine. Okay. Turbo machine. If you write the Euler's equation of turbo machine, so it is given. So first of all, that work done per unit mass flow rate called specific work, you all know, right? Now with this you will write the equation of turbo machine. So basically this equation is nothing but E is equal to torque into angular velocity T into W. Okay. And W is the angular velocity. What will be the torque? So torque is nothing but CT1 R1 minus CT2 R2. So if you take this, it will be CT1 R1 W minus CT2 R2 W. W. So W. So this is nothing but E. So the rate of energy transfer per unit mass flow per unit time, and for this reason the unit, if you check for this, okay, so the rate of energy transfer per unit mass flow per unit time, here it is nothing but the unit you may get torque into angular velocity, which is also the power. Got my point? So this, what you are writing, this is nothing but the rate of energy transfer rate of energy transfer per unit mass flow per unit time. Okay, so that's the reason once you calculate this value, and that value will be the power unit. Okay, because what actually you had started a specific work, but rate of energy transfer per unit mass, it is now specific work. Okay, but per unit time, so specific work divided by time, if you do, then it comes for the power unit. Okay, right. Now I hope this one is clear. Now we'll write the equation for the compressor. So what will be the equation for the compressor as per Euler's turbomachinery? All right. So now if you write the equation for the compressor, so obviously compressor will take work. So you can say work input to the compressor. Yes or no? Work input to the compressor you need to write. So the same formula you can use, but if you write for the axial flow compressor, so definitely axial flow compressor inlet and exit diameter will be same, or radius will be same, because it is the axial machine. Here the Euler equation of turbo machine I have given general formula, so that there is an R1 and R2 you are getting. This formula you can mold according to your machine. If your machine is axial machine, so this diameter or radius will be same at inlet and exit. Alright. Now so this one, because we have a compressor, so we can write work input to the compressor, right? We can write here work input to the compressor. So what is the work input to the compressor? Work input to the compressor, so it is nothing but W, and here it is U into CT2 minus CT1. This is the work input to the compressor. Okay. Now for this we need to write the equation, and this equation will be W U in bracket, what is the CT2? CT2 if you write in terms of alpha, so it will be CA tan alpha 2. What is CT1? It is into of CA tan alpha 1. And this is nothing but W U CA tan alpha 2 minus tan alpha 1. Okay, right. Now you know that W U CA tan alpha 2 minus tan alpha 1, that relation you have written somewhere. Check what is tan alpha 2 minus tan alpha 1. This is tan beta 1 minus tan beta 2. So you can write this tan beta 1 minus, last class nicely I had explained what is the alpha 1 beta 1, so everything you know now. So in question, what angle is what available? If they have given beta 1 beta 2, or if they have given alpha 1 alpha 2, based on that you use the formula and calculate this work. It is the input, work input. Now both formula you have, right? In terms of both. alpha and beta. Alpha I told you it is called air angle or absolute angle or flow angle. Beta 1 I told you it is the blade angle and relative angle. Okay, this value I had given to you. Already it is given in the last class. Okay. Alright. Fine. So tan alpha 2 minus tan alpha 1 and tan beta 1 minus tan beta 2. So in those format you have. Alright. Now one more factor we have, I just want to introduce here. If you go and calculate the work, so ideally this is the formula. Okay, this is the ideal. But in actual, the reduction in work absorbing capacity of stage, okay, will not be the ideal value. Why? Because there is the formation of you can say that boundary layer inside the duct, okay, where the flow is what going on. So the boundary layer formation will be there, you can say, in reality. So less area you will have, area will be decreasing because the formation of boundary layer you may have. For that reason, to compensate that reduction in work absorbing capacity of stage is taken into account by a factor known as work done factor. So this work done factor you need to multiply to this work. Actually there is the derivation. We have derivation to show that how that work done factor came into picture and how to use this. Okay, there is derivation, but I will suggest as per gate point of view, you just need to remember the formula. It is not required actually. Okay, but if you say, I will definitely give to you. Like it is not required. What I want to tell you. Okay. Right. Now, so this work done factor you need to multiply here, and I must write here. So work done factor. Okay, work done factor. So actually it will, this work done factor value at starting like first stage, second stage, it will not affect more, but once the number of stages will be increasing, so definitely because it is the compressor, so high pressure will be developing, and due to adverse pressure gradient in compressor boundary layer along the duct, that thickness of the boundary layer will be increasing. So I will show the diagrams, you will understand easily. Okay, you will understand, it's not difficult thing. The thing is I don't want to go into that because it's a like again it will become lengthier, so that I don't want actually. But anyway, I will explain you, don't worry. If you write W, what is the formula here? Okay, it is UCA tan beta 1, UCA tan beta 1 minus tan beta. Just listen carefully, it will be clear. Okay, within 4 or 5 minutes it will be clear. Now this value we can write because we have this equation, we have U, and again I'm just going to manipulate this. So you will have use CA tan beta 1 minus CA tan beta 2, this you can write. Now check the triangle, you will get. So instead of CA tan beta 1, what you can write? You can write U minus CA tan alpha 1 in one bracket minus it will be as it is CA tan V2. Check the triangle. So you will get this, how it comes, you will understand, okay? That's the reason I told you I am not going into that mathematical formulation and all, otherwise it will take so much time, because in GATE only 4 marks the weightage of this topic we have, so I am trying to finish this in very short way, in that way that you need to understand. At the same time we should finish it in very less number of hour, and that content should also very less, because unnecessary contents I don't want to give for the competition. That's my point. Even though this derivation and all not required, but just I want to like explain you how that work done factor came into picture. For that reason, this you can understand. You check the triangle and you will get it. So ultimately, if you write this equation, so here you will have, and this is nothing but u, in bracket you can write u minus, you write take common CA, and here it is tan alpha 1 plus tan beta 2. Check. Now, why I am writing in this format, it's very easy only, okay? If you write the value of u, then you will get it. It's not very difficult. The thing is you need to relate it and you will understand how this came, okay? And you do it. If you not understand, then again I will explain how it comes. Anyway, from here what you got, that relation you check. If you see this value of CA, check this value of CA. If this CA value, CA, if it is increasing, anyhow if it is increasing, then what will be the value of W? The CA will be increasing, then W value will be decreasing. Yes or no? So less work done at the region where CA is high. Okay? Less work input or work done at region where CA is high. Okay, and obviously in this sense that temperature change of temperature rise in compressor, that will also affect. I will write the stage temperature formula, then you will understand. Okay, or here I will write only, so easily you will understand. Okay, so just give me time, I will write that also. So what my point is, if you see, if you are increasing or anywhere if it is increasing, then W, that work will be decreasing. Then where is the chance of that CA increment? It's simple. If you check the annulus, or you can say duct of the compressor, suppose this is the duct of the compressor, check. This is the duct of the compressor. Just listen, you will understand easily. At the starting only, if you, this is the starting, so this is the flow is what going in this way, because one more thing you know very well, this compressor is what here stage to stage pressure is what rising, okay? So stage to stage pressure is rising, so obviously adverse pressure gradient in compressor will be there. And adverse pressure gradient will be there, so definitely we will try to increase the thickness of boundary layer. So at starting you can say this is the formation of boundary layer, but as well as it will go towards the number of stages, so this thickness of boundary layer will be increasing like this. So this is what, this is the thickness of boundary layer. Thickness of boundary layer, both side, here also thickness of BL. So this is the actual or real compressor we are talking. So now whatever the velocity of the flow, and that velocity of the flow is nothing but CA, you can say. So if you go and move forward, so here CA, check what is the area here for the duct and what is the area here. Area more, here area less, huh? Area less. So velocity more. Here area more, velocity less. That concept you know. So if you check the work input to the compressor, what is the formula? It is U minus CA tan, what was the formula? Tan alpha 1 plus tan beta 2. This is the formula. So CA is what increasing here. See, the CA is what increasing. The CA is what increasing once you go for the more number of stages. Just divide it into different parts. Okay, this is the first stage, you can say. This is the second stage, you can say. This is the third stage. No? So this CA will be increasing. Why? Because area is what now for the flow is what decreasing, because on the wall, inside the wall, that boundary layer thickness will be increasing, because this compressor, you know very well, it is working, and stage to stage pressure is what rising, so obviously adverse pressure gradient will be developed and thickness of boundary layer will be increasing. So if CA will be increasing, so this work will be reducing. Okay, so because of it, now everywhere, means from first stage to fourth stage or third stage, the work absorption is what not same everywhere. You got my point? Work absorption is what not same. Once it is going for the next stage, if number of stages is what increasing, then work input will be decreasing. So suppose it is in ideally, if it is 100 kilowatt work is what absorbing, that work capacity is what 100 kilowatt, suppose it is absorbing the work ideally, but in reality it will not be 100 kilowatt. Why? Because CA will be increasing, so work will be reducing. So instead of 100, it may be 80 or 90 kg per second or kilowatt, what you can say. Hope you understood. For this reason, we are introducing the work done factor. So the work done factor, basically it will indicates, and yes, this value will be always less than unity, and that range of the work done factor, I will give that range because sometimes it is required. Okay, so the work done factor is what basically the stage work absorbing capacity is less than that given by Euler's equation. So Euler's equation, what formula it is giving? This is the Euler's equation formula. Okay, this is the ideal here. This is the Euler's equation. This work came from the Euler's equation, and this is the ideal work. Ideal work input, because Euler's work input will be the ideal work. Okay, so now because of the formation of boundary layer, CA increasing, so work input will be reducing. So this reduction in work, I will write here. So because here, let me write. So CA increasing, so work will be reducing. Okay. From this previous analysis, hope you understood this. So now this reduction in work, this is important. This reduction in work absorbing capacity, because it's a compressor, so it will be absorbing the work absorbing capacity of the stage is taken into account by a factor known as work done factor. Okay, so it is denoted by omega or sometimes lambda. So what is the actual work? Now our actual work input actual or real work input. So this work, what is given by the Eilers, and it is Eilers work is what UCA. This formula you have, right? It is, check this one, tan alpha 2 minus tan alpha 1, or in terms of beta 1, tan alpha 2 minus tan alpha 1, or this work okay. So now to account this reduction in work, we have work done factor. So this work done factor will be multiplied here. As I told you, ideally it will suppose take 100 kilowatt or kg per second, but because of this CA increment, stage to stage, CA increment will be there, so work reduction will be there, work will be decreasing or reducing. So this reduction we need to take in account. So how you will know? Suppose at first stage it is taking 100 kilowatt, that value you got, but it is not 100 kilowatt at fourth stage. So how you will take it into account? So you just multiply it by gamma. That's all. Done. This gamma is nothing but work done factor. Hope this one is very clear to all. So what you will do, you will multiply by the work done factor. And what is the range of this work done factor? So this range of the work done factor, you need to remember, okay? It is 0.96, you can say, for the first stage, and it will go to the 0.85 stage, you just say fourth stage, just approximation I mean. Done, right? See, you can say like CA we have assumed it is constant, so why CA is what increasing? That is true. Ideally what we assumed axial machine, and for axial machine obviously this axial velocity CA will be constant, that is true. I told you for the actual compressor, if you calculate for actual compressor, if you calculate actual work input, so that time because of the formation of boundary layer, because for the actual case only boundary layer you will get, because for the real or for actual case you have to consider viscosity is there, and if viscosity is there then there will be formation of boundary layer. But if you have assumed it is ideal, so for ideal we are considering there is no viscosity. If there is no viscosity, then there is no boundary layer formation. If there is no formation of boundary layer, then CA, which is axial velocity, it will be constant from first stage to fourth stage, or you can say from first to last stage. CA will be constant if there is no formation of boundary layer. But in actual it is not. In reality we have viscosity, right? We have friction. So definitely formation of boundary layer will be there. So you cannot eliminate boundary layer in real case, but in ideal you can eliminate. You are free to eliminate. Okay, done. So this one is very clear, and believe me, that question they are asking. Okay, so ultimate, what is the formula you got for the work? And this is very special formula, and many times question they had asked based on it. Okay, so you need to remember this. Sometimes they will give that alpha 1, beta 1, alpha 2, beta 2, and sometimes they will not give. So what they will give? They will give the velocity component. And what are the velocity component? Simple, that CT1 and CT2. So suppose they have given CT1 and CT2 also, then you need to write the formula of the that work. Okay, here. So this is nothing but the work will be W. You can write U. This is the first formula, UCT2 minus CT1. What is the another formula? Another formula is in terms of UCA, which is nothing but tan alpha 2 minus tan alpha 1 is equal to UCA it is tan beta minus tan beta 2. Okay, always remember this value. Okay, all right. Anyway, now if work done factor they have given, then multiply everywhere. If they have not given, consider 1. Okay, ideally it is 1. This is the work input to the compressor. Okay, and if area is what decreasing, then velocity will be increasing. Okay, so for that reason CA is what increasing. Anyway, this part is what done. This is the work. Now we'll go for the here only we can write the stage temperature rise better, because we know the thermodynamics relation. Okay, and from the thermodynamics relation we can have this, that it is very special stage temperature rise. Stage temperature rise. Stage temperature rise is what denoted by delta T naught S. S for stage, not stator. Okay. Anyway, and whatever the temperature I am saying, it is the total temperature, or if you want to write this delta Ts also okay. Anyway, so how to get it? Simple, you know that work is nothing but specific work. So it will be what? It will be Cp delta Ts stage temperature. This work is what is specific work, so M already it is taken this side, so M will not be multiplied here. If you are writing total work, then it will be mCp delta T. Otherwise, because it is specific work, so Cp into delta T. Alright, now what is this delta T? And remember, whatever the work I am writing here, or temperature rise I am writing here, it is for the stage. And if you check rotor and stator, so stator is what between 2 to 3. No? See, basically 1 and 2 and 3, you can say this is what rotor and this is the stator. So in stator, is there any work? No. Why? Because it is not a rotatory part. If it is not a rotatory part, and even we are not adding any heat also, so this T02 and T03, this will be same or not? Total temperature will be same. Okay, so if you check across the stator, so across the stage, so what is the stage? It is 1 to 3. So I can say the stage temperature rise is nothing but T03 minus T01. Yes or no? This is the stage temperature rise. Stage temperature rise. Delta Ts will be T03 minus T01. So this T03 also will be T02 and T01. Why T02? Because T02 and T03 will be same. Because it is a stator, it's just like a diffuser only. And across the diffuser, total temperature will be constant. So you can say T02 is equal to T03. So what is the delta Ts? Delta Ts is the stage temperature rise, and this is nothing but T03 minus T01, because 1 to 3. This 1 to 3 is nothing but stage. Okay, this is stage. So T naught 3, but T naught 3 is also T naught 2. Total temperature must be constant. So T naught 3 minus T naught 1 is equal to T naught 2 minus T naught 1. So this is the delta Ts. Okay. Need to remember this. Now you have work. You have work. This is the work input in the compressor you already have calculated. So now this value you can get in terms of the alpha beta. So W is nothing but Cp delta Ts. So what is delta Ts? W by Cp. What is W? It is U divided by Cp. In bracket we can write Ct2 minus Ct1, or the same delta Ts we can write U Ca by Cp. Instead of Ct2 and Ct1 you can write Ca tan alpha 2 minus Ca tan alpha 1, or instead of this you see Cp tan alpha 2 minus tan alpha 1, also you can write tan beta 1 minus tan beta. This is the stage temperature. Okay, so this is the value, but if you go for the reality, so in reality what is the value of the work? It is nothing but value of the work is nothing but omega. You need to multiply if work done factor is given. If it is not given, you just remember this formula. I will write both. So please just remember this box from starting only. For all subject I am just giving the box, so you remember this box. Final, forget everything. Okay. Okay, or if omega is given, if omega is not given, what is omega? Work done factor. It will be done. Okay, so this is the formula you need to remember. So two formula, very special formula today I have given. It is the specific work input to the compressor. For real and ideal both I have given. Ideal means whatever the equation you got from the Eilers, and real means we have multiplied work done factor, and at the same time hand to hand I have explained what is the work done factor also. So always remember. Okay, fine. Now we'll go for the pressure ratio in stage. Today I need to finish this also. Okay, so fine. Now we'll go for the pressure ratio, that is called stage pressure ratio or pressure ratio in stage. how to get this? Simple. Now, if you go for the this value of if you go for the basically TS or HS plot, so through that you can get, otherwise it is not required also, you can understand, because in compressor I had taught you well. So anyway, I will draw the TS plot directly and try to recall that, okay, because compressor I had taught in jet propulsion, so from there you connect. If you go for the stage, so stage means what? This is the stage 1, 2 and 3. This is what rotor and this is what stator. So if you say stage means 1, 2, 3. So I can draw two pressure line, okay, and this is what ideal, this is T and this is S. You know how to draw, because in jet propulsion I had drawn many times. This is ideal straight because entropy is constant, and this is the actual. This is the actual line and this is the ideal line, because this is the compressor, so pressure is what rising. First point is 1 and this is what 3 I can say, okay, and I'm talking about the total value, so this is not 3 and this is the not 3 dash. Why not 3 dash? Because it's the ideal or isentropic. And 1 to 3, this is the actual rise. Actual rise. In terms of enthalpy, if I say, then what is the actual rise in enthalpy? H03 to H01. It is the actual enthalpy, because in compressor what happening? In compressor enthalpy will rise, enthalpy rise means temperature rise, yes or no? And H03 dash minus H01, so this is the isentropic enthalpy rise, or I can say ideal enthalpy rise. Ideal means isentropic. This relation you know, and this already I had explaining your jet propulsion subject in compressor. So now if I write what is the ideal work input to the compressor, now you can write here what is the ideal work input to the compressor. Now easily you can understand. So ideal or isentropic work input to the compressor, and we can write here actual at the same time. Actual work input to the compressor. So the change of enthalpy is nothing but what work. So what is the ideal? Ideal, if I am writing, so I will write here ideal is equal to, what is the ideal work? It is the rise of enthalpy. So what is the ideal? H03 minus H0 dash is the ideal work, and you can write this is what Cp T03 dash minus T01. What is the actual? So I can write here, it is nothing but H03 minus H01, or you can write Cp T03 minus T0. Okay. Now for the stage I am writing, for the stage, what is the isentropic efficiency? Isentropic efficiency of compressor, and I'm going to talk here it is stage, for the stage. Okay, what is the formula? That formula is eta c. Huh? What is the formula? It is W isentropic work divided by actual work, isentropic or ideal. What is this value? Cp T03 dash minus T01 Cp T03 minus T0. So what is the formula of the compressor? And we are talking stage, so better we'll write stage efficiency. There should not be any confusion. So it is nothing but T03 dash minus T01 divided by T03 minus T01. Okay. Now this we can write here T03, because T03 minus T01 we know it is what? Delta Ts. Starting only I have written T03 minus T01. For the stage somewhere I had written here delta Ts. T03 minus T01 is delta Ts, stage temperature rise. So this one we can write here. This delta Ts T03 minus T01 will be what? T03 dash minus T01 divided by eta stage efficiency. Okay, what we got here? We got delta Ts, which is nothing but T03 minus T01. Check what is this value? This is nothing but T03 dash minus T01 divided by eta stage. Alright. If I will write T01 divided by eta stage, what you will get? T03 dash T01 minus. We know T03 dash minus T01 we can replace by the pressure, and it is nothing but P03 divided by P01. This is the isentropic relation, and the power will be gamma minus 1 by gamma. We can place that this value to this value we can place here. Okay. So once you place, then you will get this value P03 P01. If you check this result, you will get 1 plus. You will get 1 plus eta stage efficiency into delta T naught S divided by T01 to whole power gamma upon gamma S1. This is very powerful formula, and they had asked in examination. Okay, they had asked in examination, so there should not be any confusion. This is the value. So this P03 by P01, also called RP. RP is the pressure ratio. Okay, RP, pressure ratio. It is nothing but P03 by P01. And we got 1 plus stage efficiency. They will give to you delta T naught S divided by T01 to whole power gamma upon gamma minus 1. Remember this equation. Also this you can write in this term also. 1 plus Eta stays. What is delta T naught S? Check what is delta T naught S. You have written here delta T naught S. It is Ts or delta T naught S meaning same. It is UCA tan alpha 2 minus tan alpha 1, or whatever the value you can write in that terms also. I'll write one, so just for your understanding. U CA tan alpha 2 tan alpha 1 by Cp, okay, divided by T naught 1 to whole power gamma upon gamma minus. Done. This is the all the analysis what I had thought initially. I will explain this. Now this was the very important points what I had explained here. Next degree of reaction is what left. So like for all, now we'll summarize this. This is the work. This is the temperature rise delta T naught S or delta Ts. It's your choice what you want to write. And RP. For all, okay, how that theory questions will be asked to you, you just check. So what I was trying to tell you, that formula of W, if you check here, what was the formula? It's omega. That work done factor is your choice. If it is given, you use, otherwise not required. But this is the actual formula. And this was UCA by Cp or UCA by Cp okay, and RP also, the big one formula you need to write, 1 plus eta stays UCA tan beta 1 minus tan beta 2 divided by, just try to connect this, Cp the whole divided by T naught 1, or Cp T naught 1 also you can write if you want. It's not a big problem. The whole power, it was gamma divided by gamma minus 1. The formula you know already. What I want to tell you, just listen. My point you need to understand. Equation already you have written, so it's not a big deal. Everything, I mean, if you relate this, all the parameters, W, delta Ts and RP, all, check what is the exam point of view theory here. This will be depending on high blade speed, or you can say blade speed better, not high, blade speed. Blade speed means U, I told you, or rotational speed. Second, check axial velocity. CA. Third is the fluid deflection. Beta 1 minus beta 2 is the fluid deflection angle. Alright, check now, just relate this. Here, see this W depends on U, W depends on CA, W depends on U, W depends on CA, W depends on beta 1 and beta 2 also, this third one. Okay, this one. And at the same time alpha to alpha 1 also, no issue. Now, delta Ts, which is the temperature rise. Suppose question, theoretical question they had given how to rise the stage temperature. So you should have to increase U, means this is also depending. Huh? Stage temperature rise. Axial velocity is also depending on it. And same thing beta 1 and beta 2 here also we have. Okay. Third, RP, how to rise the pressure, stage pressure rise, how we can maximize for the compressor, because what is our job to get result from that compressor. So our job is what, mainly to get max to max pressure rise and max to max temperature rise. That is our main job from compressor. That's the reason we are using compressor, right? To get more and more temperature rise at per stage at least, and similarly more pressure rise at per stage. Yes or no? That is our main job. So same thing if you come to pressure ratio. So see here also, if U and CA, if you are increasing this U and CA, yeah, for this, check this RP here also U and CA. So this is common for all three. So if all this value you will be increasing, so you will be getting good result. So this is the optimization of compressor. I mean, if they are saying optimize the compressor, so optimize means what? To get max to max result. That is the optimization, right? And balanced result means if something you are increasing, so because of that something you are not losing. You need to get balance benefits, called optimization. So if you are optimizing, so all three you will get more. Yes or no? All right. So that you need to remember.